Hi everyone, this is the lecture for Physics 112, Tuesday, April 7th, and today we're just going to take up the test. I wasn't able to allow Canvas to reveal the test answers at the time because it was actually possible for some people to finish and get the answers before other people even began. So rather than do that, I thought I'd just go over the test right now, and it's probably better that I do it this way anyhow because then you'll get to see how I reason things through. Okay, so let's just begin. We have the first 7 questions were about a mass attached to a spring, so it was a harmonic oscillator. So we have a mass of 300 grams, and it's attached to a spring with a spring constant of 100 newtons per meter. And as it oscillates, I tell you that it actually passes through equilibrium with a velocity of 10 meters per second. Okay, so let's go through the questions. What is the angular velocity of the oscillator? Sorry, the angular frequency of the oscillator. It turned out that the answer was 18.3 hertz. How did I get that? Well, the angular frequency, omega, is given by the square root of k over m. So that's going to be the square root of 100 newtons. Okay, and 300 grams, we have to convert that to MKS, so that's 0.3 grams like that. And if you just crunch that through your calculator, you'll get that it is 18.3 hertz. Okay, so easy enough. The next question was, what is the period of motion? And the period and the angular frequency are related this way, or possibly you might have seen it written that way. Both are equivalent to one another. And so let's just plug in our numbers here. So you've got 2 pi, so it's 2 times 3.14 divided by omega, which we found in the previous question, 18.3 hertz, like this. And just crunching that through gives us a period of 0.344 seconds, like that. Okay, and what is the linear frequency? Well, the linear frequency and the period are related to one another by being reciprocals, and so the linear frequency is just 1 over the period, and we just found the period, so that's 1 divided by 0.344, and that's going to give you 2.9 hertz, like that. Okay, so nothing very deep there. The only thing you have to watch out for is this is the angular frequency, and that's a linear frequency. In our equations, the angular frequency comes up over and over and over again, but in the lab, it's the linear frequency that actually you would measure. Okay, so that's why there's 2 frequencies there. And the 2 pi that appears inside the angular frequency, that's because behind all of this is sinusoidal motion, and the cosine and the sine have a periodicity of 2 pi. So that's why there's 2 pi's everywhere. Okay, so the next question was, what is the maximum velocity of the motion? And there you should recognize that when you know that a mass passes through equilibrium at 10 meters per second, that tells you the maximum velocity, because the maximum velocity is obtained at equilibrium. And so the answer to number 4, you don't even need any calculation. I tell you that it is 10 meters per second. Okay, and the next one is, what is the amplitude? All right, so for the amplitude, we have the V max. Okay, and that's this. So actually, I could even say here that V max, whoops, is equal to 10 meters per second. All right, we know that V max is related to the amplitude by this formula here, like that. Okay, times A. All right, so if we rearrange that because we want to solve for A, then the amplitude can be obtained from V max divided by omega. All right, and we have those quantities above. We have that omega is 18.3 hertz, like that. Whoops, that goes into the denominator. And we have that the maximum velocity is 10 meters per second, like that. And if you crunch that through your calculators, you will get 0.55 meters. But if you looked at the answers that I gave you, actually converted it to centimeters, so that is 55 centimeters. Okay, that solves that problem. And then the next one was, what is the maximum acceleration? Well, the maximum acceleration, the formula, looks a lot like the formula for the maximum velocity in terms of a, except that now it's omega squared, like that. Okay, and so we have all those quantities on the right hand side. So omega is 18.3 hertz. All right, and we have to square that. Okay, and the amplitude is 0.55 meters, like that. And crunching that through gives you an answer of 183 meters per second. All right. The last question for the harmonic oscillator was, what's the total energy? The answer was 15 joules. And how do we obtain that? Well, there's a couple of ways. You can either do 1/2 mv max squared, which is probably the easiest way to do it. Or you could even have done 1/2 Ka squared, okay, because you have all those quantities now. Well, let's just use the first one, which is the 1/2 m. The mass I told you was 0.3, and the maximum velocity is 10 squared, like that. And if you crunch that through, it gives you 15, and everything is in MKS, so the answer will come out as 15 joules. All right. So there you go. That's the series of questions on the harmonic oscillator. The next set of questions were about waves. Okay, and first we had some qualitative questions about waves. And the first one was, what is refraction? And refraction, that's when waves bend as they travel from one medium to another. Okay, so the classic example is between air and water. So air is a medium and water is another medium. A medium just means a material which is able to sustain a wave. And actually, as the light travels from air to water, its velocity changes, and as a result, the rays have to bend. Okay, and so this is known as refraction. Now, you can also have waves bending, but this is bending around corners, and that's diffraction. So when waves encounter a sharp corner, they do get clipped by the barrier, but then they'll actually start to bend around that corner, and that bending around the corner is known as diffraction, and it leads to shadows which are not sharp. Okay, they're going to be blurry at the edges because the waves are bending around the barrier. Okay. Interference, another phenomenon that waves exhibit, are when you have two or more sources. Okay, so but at least two sources, and the waves from the two sources will meet, and they can either enhance or annihilate one another. So there are regions of space where you'll always have a situation where a crest will meet a crest, and that will give you a bigger crest, or a trough will meet a trough, and that'll give you a bigger trough. And those are regions of enhancement. Okay, and so that means like brighter if it's light or louder if it's sound. But there's also regions of space where crests will meet troughs, and whenever a crest meets a trough, you get annihilation. They'll actually cancel one another out, and so that means dark if we're talking about light, or it means quiet if we're talking about sound. Okay, and so the next question was to make use of the wave formula V is equal to lambda F. Okay, so I tell you that in music you have a frequency range from middle C to tenor C, which is the next octave up. And middle C is at 261.6 hertz, and tenor C is at 523.2 hertz. And I want to know the range of wavelengths this covers. And it turns out that the answer is 0.65 to 1.3 meters. How did I obtain that? Well, if you take this equation here, V is equal to lambda F, okay? And we're trying to solve for lambda, so just rearrange it so that you isolate lambda on the left-hand side. So lambda is going to equal V times F, all right? So let's use that equation. We have to use it twice because once for the middle C and again for tenor C, okay? And so the velocity, well, here we're talking about sound. And sound is a wave that travels in air. And I gave you this link which was a link for a bunch of constants, okay? And so here they are, and we want this information right here, okay? That the speed of sound in air is 340 meters per second. So let's put in 340 meters per second for the velocity of the sound. And for the frequency, we'll pick this one right here first, the middle C frequency, like that. And this is in hertz, like that. And crunching that through your calculator, you get 1.30 meters, like that. Okay, so there you go. There's one of them. Now the next one, it's the same, but actually here, instead of 261, you put 523.2, okay? And that actually gives you 0.65, like that, okay? It turns out that this frequency is exactly twice that frequency, and so this wavelength is exactly half that wavelength, all right? So our range from the from the shorter wavelength to the longer wavelength is 0.65 to 1.3 meters. 11. Question number 12 is basically a question for refraction. Actually, 12 and 13 are refraction, and there's the formula. The answer was 16.4. Let's see how we can arrive at that. Okay, so what do we have here? We have a pane of glass in air. Okay, so the two materials are air and glass. So number one is going to be air. Let's use the subscript 1 to refer to air, and the subscript 2 to refer to glass, like that. And now let's start substituting in numbers. So this is Snell's law here. So N1 should be the index of refraction for air. The index of refraction for air, I don't think I gave it to you, but you should know that that's 1, okay? All right, and sine of the angle that it makes in the air. Well, do we know what angle it makes in the air? So if it doesn't quite say it, but if you read it carefully, if the beam of light impinges on the pane at 25 degrees to the normal, then what angle does the beam make to the normal inside the glass? So the 25 degrees is actually in the air, okay? And the index of refraction of glass is 1.5. So put 1.5 there, like that. Sine of, and we don't know theta 2. That's what we're trying to solve for. Okay, like that. And I'm not gonna, I won't bore you with the algebra, but basically what you need to be able to do is take the inverse sine. I think most people know how to do that, so I just won't bore you with those details. I'll just give you the answer here, like that. It'll turn out to be 16.4 degrees. Okay, so there you go. In air, we have 25 degrees, and in the glass, we would have 16.4. Remember that the ray or the beam of light will always bend towards the normal in the material with the higher n. Okay, so lower n, 25 degrees, higher n, 16.4 degrees. Okay, now we repeat this, but now we submerge the pane of glass in water. And if the beam impinges at 25 degrees, now that's 25 degrees in water, what angle does it make to the normal inside the glass? Okay, so it's really the same problem, but now 1 refers to water and 2 refers to glass, like that. Okay, and if you look up the index of refraction of water, it's 1.33. So we'll put 1.33 in there, like that. Okay, sine, and the angle in the water is 25 degrees, and N2 is glass, 1.5, and sine of, and we don't know what this angle is. Once again, you would work this all out, and what you would have is basically all of this would work out to some number, and you'd have sine is equal to sine of theta 2 is equal to that number. You'd have to take the inverse sine, and you would find that that's equal to, the answer was 22 degrees. Okay, now if you're having difficulties doing the inverse sine on your calculator, I really can't help you too much, because every calculator does it in a slightly different way. Like I could even show you on here how to do it on the calculator that I have on for my desktop, but I don't know if that'll help. Okay, so you know, like You know that the sine of 30 degrees is a half, so just make sure that the inverse sine, when you do the inverse sine of a half, that it gives you 30 degrees, and you know that you're at least doing it right for that angle. Okay, so let's move on. All right. This question here was about interference. Okay, whoops. Okay, was about interference. So I have a laser, and the laser produces a light of 600 nanometers, and I think that's kind of in the red spectrum. And we shine the beam through a pinhole. All right, so it's a single hole, pinhole, with a diameter of 1.5 micrometers, and we get a bright dot with a bunch of bright and dark concentric rings about it. Okay, and this is the typical diffraction pattern of a single slit. All right, and then I ask some questions. So we know it's single slit because it says pinhole there. Okay, so we've got just one hole. Okay, if we had two holes or two slits or two openings, whatever, then it would be a double slit situation, but we only have one, so we're in a single slit situation. And so the formula for single slit is this one right here. Okay, and it's only for the dark bands. All right, and so I asked the question, at what angle does the first dark ring occur? Okay, so let's take a look at that. And let's substitute in the numbers. And we have A here. A is the size of the hole, which is that. Okay, 1.5 micrometers. Now, this is kind of an easy problem, but if you don't remember what micrometers are and nanometers are, then you're in trouble. A micrometer is times 10 to the minus 6. Okay, meters, like that. All right. And theta is what we're solving for. All right. And n is going to equal what? N is going to equal 1 because I asked for the first dark ring. And so the first dark ring, that's n equals 1. And then finally, lambda is equal to 600 nanometers. And you need to know that nano is times 10 to the minus 9 meters, like that. Okay, so if we put all those numbers in here, we're going to have for A, we'll have this. Okay, sine theta, well, we don't know theta. That's what we're solving for. All right, and n is 1, and lambda is that. All right. Okay, now divide both sides by the 1.5 times 10 to the minus 6. Well, the 1 is just going to go along for the ride, so it's not going to change your answer. So divide that like that. Okay, and what do we have now? Well, let's be careful here. We have the 10 to the minus 9 on top and 10 to the negative 6 here. So the way I like to do this, you could do it directly on your calculator, but an easier way is, you have 600 divided by 1.5. So let's just isolate those two numbers, okay? And then we have times 10 to the, and we have negative 9 on top here in the numerator, and minus 6 in the denominator, but because you're dividing, that's going to be plus 6, like that. Okay, and so this is going to equal, let me bring up my calculator. It's an easier calculation, but might as well just do it. 600 divided by 1.5 is 400. Okay, times 10 to the negative 9 plus 6 is minus 3, like that. And so basically we have to move the decimal over 3 to give you that. So to give you 0.4. So basically you have this is equal to 0.4. And once again, to get the theta, you have to do the inverse sine. Okay, I mean, I can write it out, but I just, like I said, I can't really show you how that's done on your calculator, because every calculator is slightly differently. But it looks something like this. It's inverse sine of 0.4, and the answer turns out to be equal to whoops, 23.6. All right, so that was the answer for that one. Okay, let me just check that. Yep, that's correct. Okay, a little bit of a round off, but not much. Okay, now the second one is, if you know how to do the first one, you should be able to do the second one. The only thing is you need to know that the second ring occurs at n is equal to 2. Okay, so everything is the same here, except now we're looking at n is equal to 2. Okay, and proceeding in the exact same way, you would take the inverse sine. You find that the angle turns out to be equal to 53.1. And so that was the answer for that one. All right. Okay, let's continue. Number 16, 17, 18, and 19 were about the vibrating string. Okay, and so I give you a string which is 3 meters long, and if you were to weigh this string, it has a mass of 150 grams. Okay, so 3 meters long of the string has a mass of 150 grams. We're only going to tie down 20 centimeters of it. That's the only amount that we're going to allow to vibrate, and we're going to apply 500 newtons of tension. Okay, and I ask a series of questions. So the first question I ask is, what's the linear density? And the answer is 50. Okay, well, how did I get that? Well, the linear density is just the mass divided by the length. So the mass is 150 grams. Okay, and the length, though, you've got two lengths here, 3 meters and 20 centimeters, but you have to ask yourself, what's doing the, what has the mass of 150 grams? Well, it's not the 20 centimeters. The whole 3 meters has mass of 150, okay? And so divide that by 3 meters, and you get an answer of 50 grams per meter, like that. Okay. Now, I didn't convert it yet to MKS, but for the next one, you will have to convert it to MKS. So I gave you a bunch of answers, and they were all in grams per meter. Okay, so it's a pretty easy number to divide. It's just like 150 divided by 3. So you should have seen that right away. But you will have to convert this to kilograms per meter, and that just means dividing by 1,000, like that. And that's the number we're going to have to use in the next problem. Okay, so the next question is, at what speed do these waves travel? The answer was 100 meters per second, and that's obtained by just doing the square root of the tension divided by the linear mass density. Well, we have the tension. I gave it to you as 500 newtons right up here. You can see it there, 500 newtons. Okay, and so if we put 500 newtons in there, divided by 0.05, like that, and that's going to be the square root of, like that, 10,000, and the square root of 10,000 is 100, and everything's in MKS, so the answer will come out in meters per second. All right, so there's that answer. All right, now what? Well, the next thing I asked you was what's the lowest frequency at which the string can vibrate, and that's given that by the formula F1, which is the fundamental frequency, is equal to the velocity of waves in the string divided by 2L. Well, the velocity we just determined was 100 divided by 2 times this L. Notice I call this capital L and that little l there, like that. And the reason I did that is to distinguish between, having a length L, little l, which has mass m, and tying down a length capital L. Okay, and so over here, capital L is going to be the 20 centimeters. Okay, and so let's take that 20 centimeters there and put it in, whoops, put it right there. But we want to do this in MKS, so you need to convert that to meters. 20 centimeters is 0.2 meters, like that. Okay, and so if you work that out, that gives you 250 And everything is in MKS, so that's per second or hertz, like that. Okay, so that's the lowest frequency at which the string will vibrate. It basically has two nodes at the very end and just like a bubble in the middle, an antinode in the middle. Okay, and now all of the harmonics or the overtones are basically integer multiples of this, and so the second highest frequency, okay, the second highest frequency at which the string will vibrate would be 500. And that's really simple because all you do is you say, well, F2 is just going to be 2 times F1, and that's 2 times 250, which is 500 hertz. Okay, easy enough. All right. Okay, next. We have two guitar strings, okay? And one of them is vibrating at 110 hertz, and the other one is vibrating at 114 hertz, okay? And the first question I ask you is, what is the frequency of the resulting note? Okay, so this is a situation where you have two frequencies that are close to one another but not exactly equal, and you're going to get the beating, but the beating is the slow frequency. It's the frequency at which the entire note goes loud and soft, loud and soft. The frequency of the note itself is actually the average of the two frequencies. And that just means, 110 plus 114 divided by 2, and that's going to give you 112 hertz. Okay, and that's the answer for that one. Now, the frequency that you actually hear the note go loud and soft, that's called beating, okay? So that turns out to be 4 hertz, and it's just the difference between the two. And in absolute values, because it doesn't matter which one's bigger than the other, so we'll just take the bigger one, 114, minus 110, and that just gives you 4 hertz like that, okay? And that's not the frequency of the note, that's the frequency at which you hear the thing go loud, soft, loud, soft, loud, soft, loud, soft. Actually, took a look on Wikipedia because sometimes they have recordings of these things, and sure enough, they had a very nice recording. And I thought they had a really good explanation of why you hear this beat frequency. So I thought I'd just throw that reference in there. Okay, so you could take a look at the Wikipedia page on beating, and it's very good. All right, so let's move on. Um, Question 22 here. An alarm has sound intensity of 20 milliwatts per meter squared at a distance of what meter? What is the intensity at 2 meters? Okay, and the answer is 5 milliwatts. And you go, why? Well, this is the inverse R squared law, and I made it as intuitive as possible. Basically, if you're going from 1 meter to 2 meters, what are you doing? You're doubling your radius. Okay, so if your radius doubles, so you do 2 times the original radius, then what that means is that the intensity will actually decrease by r divided by 2 squared, okay? In other words, it'll be 1/4 the intensity. And you say, well, why is it 1/4 the intensity? Because the intensity decreases as r squared. So if it's twice as far, it's going to be twice squared, or 1/4 the intensity, okay? And so all you have to do is divide by 4, and that's going to equal 20 divided by 4, which is 5, and the units are milliwatts per meter squared, okay? A watt per meter squared is really loud, okay? It's almost at the point of like pain. So, for human hearing, like milliwatts per meter squared are more typical numbers, okay? So, question 23 was about intensities in decibels, okay? And this is the formula right here that converts between um, linear intensities and intensities in decibels, which is a log scale. And let me just tell you what the numbers are in here. That's the intensity in watts per meter squared, so it's exactly like the intensity up here, okay? All right, same units. All right, I naught is a reference, which we actually don't even have to worry about because it just drops out of the equation. But if you wanted it, usually for sound, this formula is actually applied to other things too, to other signals, not just sound signals. But for sound, people usually choose 10 to the minus 12 watts per meter squared, and that is the quietest possible sound. that the human ear can hear, okay? I mean, there are sounds quieter than that, but the quietest sound the human ear can hear is in the range of 10 to the minus 12 watts per meter squared, okay? And so you won't need it in the problem, but I mentioned it in passing, okay? So now we could just take this equation here and say, okay, well, if this is true for one, one alarm, okay? So let's say beta 1 here is equal to I1, all right? Where, let me just isolate that. What's this I1? I1 is the intensity in watts per meter squared of one alarm, okay? And beta 1, that's the intensity of one alarm, but in decibels, and I gave you that. It's 44 decibels, okay? Like that, all right? Now, great. The decibels do not add. So if you did something silly like, 4 of them, you just take 44 and you multiply it by 4, that's going to give you the wrong answer. Okay, I went through that a lot of times, so I won't do it again. It's I that will quadruple, that'll multiply by 4. So if you want the intensity of 4 of these things, you need this intensity here for 4 of them. But that one is easy because the intensity of 4 of them is just 4 times the intensities of one of them. Okay, the I's are perfectly linear. They're like any other unit you've ever dealt with. Okay, and so if you have one alarm and it has intensity I1 and you have 4 of them, then it's going to be 4 times I1. Okay, and so we have that. So let's put this here into that right there. Okay, so on the next line, instead of I4 here, all right, let's replace that with 4 times I1. So 4 times I1 like that. All right, and let me group those two together. Put that over there like that, okay? And at this point, we're going to make use of this log identity. Log of A times B is equal to log of A times plus log of B like that, okay? So what's happening here is between A and B, you have a multiplication going on. Okay, so if you do A times B first, and then you take the log, that's going to give you the same answer as taking the log of A, then taking the log of B, and then adding them together. Or the way I think about it is the log just distributes. It distributes over A, and then it distributes over B. But in doing that distribution, it changes multiplication into addition like that. Now this is a property of logs, which you can just, which you should have seen, okay, or you can look up, all right? So how am I going to use that? Well, there's this 10 in front, okay? So the 10 is just going to go in front of both of these terms here. Like if I had a 10 here, well, then there's going to be a 10 here and a 10 there, okay, like that. Because it's just like multiplying everything by 10, okay? So over here, what I'm going to have is 10 log of 4. The log is going to turn the multiplication into addition. I still have that 10 log of that. All right. And now you take a look at this and you go, well, what has this got me? That is exactly this. Okay. So this is basically to the intensity in decibels of just one of them. And so on the next line, I can say, all right, well, this I can just replace with beta 1. And I told you what beta 1 is. Beta 1 is 44 decibels. And so now you get that this is equal to 10 log of 4 plus 44. Well, 10 log of 4, you can do that on your calculator. It'll turn out to be 6. Okay. And that means that the answer is 50 decibels like that. All right. So there you go. There's the answer for beta 4. All right. The next two problems were about Doppler effect, okay? And in one of them, you're standing still and the car is approaching you. In the second one, and the car has the horn blaring, okay? And so the car is the source. So you, the receiver, are standing still and the car, the source, is approaching you. In the second one, the source is standing still and you, the receiver, are approaching it. So it's the other way around, okay? Now, for both of these, you use this formula here, But you got to be careful because you got to know, well, do I want the plus or the minus? Okay, so let's work through that. First, this F naught, that is the frequency that you would hear if no one were moving. Okay, if there were no Doppler shift at all, then you would just get 1,000 hertz. Okay, and I even said that this is the frequency that would be heard if the car were not moving. Okay, so 1,000 hertz. All right, now the next one is the V by itself, and you can see there's a V right there, and there's a V right there. That V corresponds to the speed of the waves in the medium. In this case, 340 meters per second, because it is sound. Okay, and VR is the receiver. And you say, okay, what's VR equal to? VR is the receiver. Well, you are the receiver, and you're standing still, so that's 0. Okay, and the source, that's the car, is driving towards you at 40 meters per second, like that. Okay, so there you go. Now, if you take this equation and you plug all those numbers into it, F naught, that's 1,000. The V's here, they're 340. Whoops. And 340 here, like that. Okay. Now, it's plus minus VR. We have to choose whether to plus or minus, but it's 0. VR is 0. So it doesn't matter whether you're adding or subtracting 0. Okay, so you don't have to make any decision in the numerator, but in the denominator you will. Okay, so this one is the source is moving at 40 meters per second, and the question is, do you want the plus or the minus? Okay, well, if you chose the plus, like that, what would happen is your denominator would be bigger than your numerator, and you would get a number less than 1,000. So that's wrong. It has to be greater than. Why? Because when the source is, so that's the car, when the source is approaching the receiver, okay, the frequency goes up. All right, so in other words, when like a car that's blaring its horn is approaching you, you hear a higher frequency than you would if it were standing still. So you want to subtract there, and that's the way I make the decisions. I just say, look, do I expect the frequency to be higher or lower? Well, then choose the sign that will give me the higher or the lower frequency accordingly. Okay, and if you work that out, the answer turned out to be 133 hertz, like that. Okay. Great. So in the second one, I just wanted to make sure I gave you a second problem on this to make sure that you understood the difference between VS and VR. It's the same formula, but and almost the same quantities here, like this. But now the source is the car blaring the horn is standing still. Okay, so the source is standing still, but the receiver, you're the receiver. You're driving towards it at 40 meters per second. Okay, so basically it's the same thing, but whereas over here we had VR is 0 and VS is 40, here we have VS is 0 and VR is 40. Okay, and so let's plug into this equation here, like that. All right, so F0 is 1,000. V is 340, that's the speed of sound. Okay, and over here too we have 340, like that. Okay, and now in the denominator, Vs is 0. So again, it doesn't matter whether you do plus 0 or minus 0. No decision to be made there. Over here, well, the source and receiver, they're approaching one another. Okay, so whenever they're getting closer, no matter which one's moving, the frequency is going to go up. Again, you expect the frequency to increase. So that VR is 40, but in order for it to increase, this time you need the plus. If you put the minus in there, you'll get a frequency lower than 1,000, which is wrong. So you want a frequency higher than 1,000. So there you go. All right. And this time it turns out to be 118 hertz. And it's funny because if you compare these two numbers, you'll see that it's a big difference. I mean, in both cases, the source and the receiver are getting closer at 40 meters per second. But if the source is moving, you get a bigger Doppler effect than if the receiver is moving. Okay, so there you go. All right, question number 26 was about thermometers. And so I ask a question, how much does a 5-meter bar of some material expand if it is heated from 10 degrees Celsius to 50 degrees Celsius? And I tell you that the coefficient, the linear coefficient, sorry, that should be coefficient of linear thermal expansion. So I think it's kind of obvious, but that should be there. Okay, linear thermal expansion, and I gave you that number there like that. So over here, what are we asking for? Well, I want to know how much does the bar expand? Okay, so what's the expanding? That's your delta L. Delta L is how much did it grow? How much did the L change? Did it expand? Okay, and so we're solving for delta L. All right, and I gave you everything else. So this is a pretty trivial problem. It's just a matter of plugging in the right units, numbers in units here. Okay, so we have this here like that. All right, so there's your coefficient. And L naught is the original length of the bar, which I told you was 5 meters. And your delta T, that's your high minus the low temperature, 50 degrees Celsius minus 10 degrees Celsius, like that. Okay, and you'll notice that this per degree Celsius here, that's going to cancel these degrees Celsius there and there. Okay, and the only thing you're left with are meters, which is what you expect. And the answer that you get is 0.0462 meters. And the answer, to get it right, you have to convert it to match it with the answers I had. You had to convert it to 4.62 centimeters, like that. Okay, now that's actually pretty big expansion. Things don't normally expand that much, but it's not atypical for some metal over that temperature range to expand like a few millimeters. Okay, maybe even like half a centimeter. Okay, yeah, it is a noticeable effect. Okay, so there you go. All right. So I should just note something, like during a test, I will pick a particular problem, but there's other variations to this problem, which we did. And so like on the final, make sure that you study all the variations because, I could do different things here. Like for instance, I could give you delta L and ask you what delta T is, or I could give you both delta L and delta T and ask you to calculate alpha, which is basically the process that you do when you calibrate a thermometer. Okay, let's go on here. So question 27 is ideal gas law. And here I have a gas which occupies 2 liters at 3.75 atmospheres and 300 Kelvin. What volume does it occupy at 1.5 atmospheres and 400 Kelvin? And the answer is 6.67 liters. And you go, okay, well, how did you get that? So you could do this in a couple of ways. Like you could first solve for the number of particles and then use that again to solve for when you've got like a different volume and a different pressure and temperature. But this is the way I showed you in the review session, and this is by far the easiest way to do it because you don't have to convert everything to MKS units. Okay, and so basically, PV over T, that ratio remains unchanged when you move from one state to another. Okay, and so this is the easiest way to do it because then I don't have to change my atmospheres to pascals. I don't have to change my liters to cubic meters. And the temperature has to be in an absolute scale, and we've only studied one absolute scale, so it has to be in Kelvin. And I made life easy for you. I didn't do Celsius, but if I given you Celsius there, you would have had to add 273 to convert to Kelvin. Okay, and so if we just plug in the numbers here, so you could say P1. That's like your initial state. And I'll even put in the units just to show you how they all cancel out, how they all work out. So, your initial state is at a pressure of 3.75 atmospheres. Your initial volume, V1, that's going to be 2 liters, like this. Okay. And your initial temperature was 300 Kelvin, like that. All right. And that gives you the left-hand side. On the right-hand side, I tell you that the new pressure is going to be 1.5 atmospheres. I want you to calculate the volume. I say, what volume does it occupy? So I want you to figure out V2. And the new temperature is going to be 400 Kelvin, like that. Okay. And I won't bore you with the arithmetic. You just work that out. And you get that V2 is equal to 6.67 liters. Okay, and at no point did you have to make use of the fact that like 1 atmosphere is equal to 1.012 times 10 to the 5 pascals. Okay, so I mean, not that that's difficult, but it's just kind of annoying, especially in the context of a test where you might make mistakes in doing that conversion. So there you go. If you've got like the gas at one state, so 1p, 1v, and 1t, and it changes to another p, another v, and another t, okay, you could just use the ratios there, and you don't have to worry about the um, the units. Okay, once just to remind you why this works, because either case this is going to equal the number of particles. The number of particles doesn't change. Okay, so that remains the same. And of course, you need the Boltzmann's constant in there, but that's just a constant. Okay, so because the number of particles doesn't change from the first state to the second state, this is going to equal that ratio. And it's going to equal that ratio. Well, that means that these two ratios have to be equal to one another. Okay, there we go. So next one, number 28, was a specific heat problem. I basically ask how much energy does it take to heat up 300 grams of water from 20 degrees Celsius to 75 degrees Celsius. Okay, and the answer is 80.6 kilojoules. Let's see how we work that out. So I'm asking for how much energy? Well, that's your delta U. The reason we call it delta U is because it's how much energy you have to already add to the water. The water already has some energy at 20 degrees Celsius. It actually has quite a bit of energy at 20 degrees Celsius. But we want to add more. So we want to add to it. In other words, we want a delta U, add a delta U to it to get it up to 75. And that's going to equal M, which is the mass of the water, which is 0.35 kilograms, converting to MKS. The specific heat of water, so I think I gave it to you. It's an easy number to memorize because you tend to see it a lot. It's this, okay? So that's 4,186 joules per kilogram degree Kelvin, all right? And the delta T is, well, it starts at 20, goes up to 75, so it's going to be 75 minus 20 degrees Celsius, okay? Now, it might be a little confusing. This is Kelvin and this is Celsius, but remember that a Celsius degree and a Kelvin degree are actually exactly the same size. Okay, the only difference between the Kelvin scale and the Celsius scale is where does the zero start? And in the Kelvin scale, the zero starts at absolute zero, whereas in the Celsius scale, it begins at the point where water freezes. But if you say, the temperature of this room went up by 1 degree Celsius, that's exactly the same as saying that the temperature of this room increased by 1 degree Kelvin, okay? And so don't let that be confusing. The size of the degree as a measure of temperature change are identical. It's just where does the zero of the scale start? Okay, so the Celsius and the Kelvin will cancel, all right? And here we've got a kilogram and the amount of water, and that's going to cancel this kilogram there, and all you're left with are joules. Okay, and if you work this out, it's going to turn out to be 80,600 joules, and it's pretty typical to work in kilojoules. All right, you'll actually see that like on food products in Europe or even in Canada, and maybe sometimes in the US, although I usually see calories in the US. You say how much energy is in this food, and it might say like 100 calories, but it might actually give it to you in kilojoules. So kilojoules is a pretty popular unit, and you should be able to convert between joules and kilojoules, and so the answer is 80.6 kilojoules. Okay, now the next one, number 29, is actually a phase transition, okay? And so I have a bag of ice which weighs 10 kilograms, and I want to convert that ice to water, okay? I want to melt it all right? Now, I wasn't totally explicit in this problem, but I think it was kind of clear from the context. When you do these phase transitions, you start with ice at 0 degrees Celsius, and you add heat, you add heat, you add heat. You don't get ice at 1 degree Celsius, 2 degrees Celsius, or whatever. You get ice converting into water at 0 degrees Celsius. So halfway through the phase transition, you'll have some ice at 0 degrees Celsius and some water at 0 degrees Celsius. And then at the end of the phase transition, you'll have all water at 0 degrees Celsius. So all through the phase transition, the ice water stayed at 0 degrees Celsius. It's simply changing form from ice to water. Okay, so there's no delta T in there because delta T would be 0. Okay, so we just have that delta U, the energy we need to add is the mass 10 kilograms, okay, multiplied by the latent heat of fusion. All right, so let's look at our constants here. I give you the latent heat of fusion of water, and I also give you the latent heat of vaporization. You wonder, which one do you need? Fusion is the solid-liquid transition. Vaporization is the liquid-gas transition. So you need this number right here. All right. And I guess the K in kilograms should be capital. All right. And you can see here that the kilograms are going to cancel out. All right. And all you're left with are kilojoules. And you get 334 times 10. So 3,340 kilojoules, which you can move the decimal over 3 and write that as 3.34 megajoules, which is a lot of energy. So the next time you go and buy a 20-pound bag of ice, okay, and you use it in your cooler and it takes forever to melt. You wonder, why does this ice take forever to melt? Because it needs to absorb a lot of energy from the environment before it melts. Okay, so ice is pretty good as a refrigeration, like in a cooler, because it just takes that much energy before it finally melts. Okay, all right, so let's move on. The next two questions were about the relationship between kinetic energy and temperature. All right, and so I don't know, I just had to pick some temperature, so I picked the surface of the sun. Okay, and so the surface of the sun is at 5,778 Kelvin. All right, and I asked the question, what is the typical energy of a gaseous particle at that temperature? I don't even care what kind of a gaseous particle it is. It doesn't matter if it's a proton, which is what I ask here, an electron, or helium or hydrogen or whatever. Okay, because every particle has the same average kinetic energy at a given temperature. All right, so here's the formula. The average kinetic energy is 3/2 times K Boltzmann times T. All right, and it's just a matter of plugging in. So that's 1.5. K Boltzmann, I gave that to you, and it's right there. Okay, so let's copy paste that in here. All right, it's 1.38 times 10 to the minus 3, so it's a very small number of joules for every degree Kelvin. Basically, K Boltzmann, what it is it's a constant which converts from Kelvin to joules. Because in our analysis of ideal gases, what we discovered was that temperature is an energy. It is a measure of energy. It's a measure of the average kinetic energy of the particles. Okay, so we could go around measuring temperatures in joules, but no one's going to get away from the Kelvin scale or the Celsius scale. They're here to stay, or the Fahrenheit scale. We're going to keep using that. But if we wanted to, we could get rid of those and just measure, temperatures and energies in joules. Okay, and then finally, okay, so there was the 3/2. There's the K Boltzmann, and the temperature, I already gave it to you in Kelvin. Okay, and so there it is. And if you multiply that all out, you get that energy there. Now that's a very tiny energy, 10 to the minus 19 joules, but these are tiny particles. Okay, we're talking just like atoms here. Okay, and in the next one I say, what is the typical speed of a proton at the surface of the sun? Well, as you can imagine, at the surface of the sun you're going to ionize things quite a bit. So if you have a hydrogen, that's going to just get torn apart, and you could have this bare proton floating around. Okay, and so the question is, what's V? All right, we want to find V because it's a typical speed. Well, you have the kinetic energy. There it is. Okay. You have M, but in the wrong units. You have M as 1 atomic mass unit. Now, if you didn't know that, if you take a look here, 1 proton is 1 atomic mass unit, and it's equal to 1.66 times 10 to the minus 27 kilograms. Okay, so all you had to do was just look up the mass of a single proton, and I guess that's probably why I chose a proton. I just said, let's just do a proton, so that you just use the number 1.66 times 10 to the minus 27 directly. Okay, and all right, well, let's substitute in for the kinetic energy here. I'm going to substitute in that number, and that's got to equal 1/2 times the mass times V squared, like that. Okay, so I'm not going to bore you with the details here, but basically you would divide that side by that, and then take the square root, and you would find that you would get 12,000 meters per second. Okay, and that's really fast. That's extremely fast. In fact, you can move the decimal over 3, and you had to match the answer. It was 12 kilometers per second. Okay, so yeah, 12 kilometers every second. All right, that's how fast protons are moving at the surface of the sun. All right. And then the remaining questions were about the second law of thermodynamics. And so let's take a look at them. One of them was, do you just understand the second law from a conceptual point of view? And I gave you a bunch of answers. I've repeated them all here. And I asked you which one is false, which one is incorrect. So let's go through them all, okay? So the first one says, can heat spontaneously flow from a hot area to a cold area? If you put something hot beside something cold, which way is the heat going to go? It's just going to naturally go from the hot to the cold. So that one's true. Okay, no problem there. Systems go from order to disorder. That's right. That's kind of a microscopic way of thinking of the second law of thermodynamics. Okay, so if you have like things which are in an ordered state, as time goes on, the energy will jiggle them and then it'll disorder them. Okay, and the opposite does not happen. You don't get things going from disorder to order. An example is that I always give is coins in a box. If I have like a million coins in a box and they're all heads up, and then I shake the box, give it a little bit of energy, then they'll fall and they'll be about half heads up and half heads down. Not exactly, but approximately. Well, I can keep shaking the box over and over and over again, and they'll always fall about half heads up, half heads down. What are the chances that I shake the box and then they'll fall all heads up? So they went from like half and half to all heads up or all tails up. Well, highly, highly improbable. In fact, if there's a million coins, the probability would be 1 divided by 2 to the exponent 1 million. Okay, and if you do that number on your calculator, you're going to get 0. So it's astronomically improbable. Okay, the next one was Newton's laws are symmetrical in time. Yep, I made a big deal about that. That it's only the second law of thermodynamics which is not symmetrical in time. Okay, so the second law of thermodynamics is sometimes called time zero. It points towards forward times because things are always going to disorder, never the other way around. Okay, Newton's laws, no, they're symmetrical in time. If you like watch a billiard ball bouncing off of the bank of a pool table or something like that, you run that movie backwards, you can't tell that the movie's running backwards. Okay, so the only one has to be this one. Heat can spontaneously become work, and that's correct. That one's false. Okay, so that's the correct answer. It's false, because if that could happen, the room that you're in right now has a lot of heat. Okay, could you imagine that heat suddenly lifting things up? That's what work is, like when you lift something off the ground or off the top of your table, that's work. Could you imagine the heat in the room, the heat in the air, lifting things up and moving them around? I mean, be bizarre. So this just does not happen. The word spontaneous is important there because you can have heat do work, but only in the state where heat is trying to flow from a hot area to a cold area can you siphon off a little bit and make work, and that's what a heat engine is. Okay, and the last 3 questions were about heat engines. All right, so we have here a manufacturer that claims that they can build an engine which absorbs 10 kilojoules of energy from a 150 degree source. Okay, so it absorbs 10 kilojoules from a source which is at 150 degrees Kelvin, and it loses only 2 kilojoules to 300 degree Kelvin, okay, with each cycle of the engine. So the first question I ask is, what is the Carnot efficiency? Okay, and the answer is 40%. How do you get that? Well, here's the formula. The Carnot efficiency is basically equal to 1 minus the low temperature, that's the temperature to which you lose energy, and in this case that's 300 Kelvin. Okay, and these numbers have to be in Kelvin. They're just like in the ideal gas law. In fact, Carnot derived this from the ideal gas law. Okay, I didn't do that derivation, but you can derive that from the ideal gas law. So since T's have to be absolute temperatures in the ideal gas law, they have to be absolute temperatures here. And the lower temperature here is, the lower is 300, the higher is 500, like that. Okay, and that's going to equal 0.4 or 40%. Okay, so there's the answer. Now, what's the true efficiency? Well, all right, let's do that. Now here, the true efficiency is basically 1 minus the amount of energy that's lost to the cold area, which is 2 kilojoules, okay, divided by the amount of energy absorbed from the high, like that, okay? If you work that out, that works out to be 0.8 or 80%, okay? So the company, the manufacturer, is claiming that the true efficiency of this heat engine is 80%, which would be remarkable, okay? And so is the manufacturer telling the truth? Nope, they're not telling the truth. They are lying. Why? Well, because the second law of thermodynamics, again, I didn't really prove this, but Sadi Carnot, using the ideal gas law along with the qualitative statements of the second law of thermodynamics that heat can't spontaneously do work, showed that any efficiency, any true efficiency of an engine must be less than the Carnot efficiency. The Carnot efficiency is like the ideal, and you can never go past it. Well, take a look here. The Carnot efficiency is 40%, so Carnot says, no, you can never get past 40%, but the manufacturer is claiming they can do 80%, so that can't happen, okay? If they could, then it violates the second law of thermodynamics, and that just doesn't happen. Okay, guys, there's the test. Um,